All right, today we want to continue talking about solids of revolution. Remember, the game is we're finding the volume of a solid by rotating a region about an axis being any horizontal or vertical line, not just the X or Y axis, even though the first example I did was rotating something about the Y axis. All right, let's consider the region. Consider. Let's consider the region bounded by the graphs of y equals x squared, y equals 9, and the y axis. This is the same region that we used last week. So that region in there. So last week we found the volume of the solid formed by rotating this region about the y-axis. Remember that the strategy that we used was to form slices that are perpendicular to the axis of rotation. Slices that are perpendicular to the axis of rotation will form circles. Now we just take the cross-sectional area of the circle and multiply by the height. So the big idea here is find the volume of the slice by taking the cross-sectional area and multiply by the height. We sliced perpendicular to the axis of rotation. So in this case, the cross-sectional area was a circle. The cross section is a circle when we slice perpendicular to the axis of rotation. So the volume of the slice was pi r squared times h. And because the circles are getting thinner, we got this stack of circles that are getting thinner. H is the delta variable. H is the delta variable since the circles are getting thinner. So it's just cross-sectional area multiplied by the height. Then all we have to do is label the radius and write the radius in terms of the delta variable. To that, we write the radius in terms of the delta variable. And we write the radius in terms of the delta variable so that the expression is all in terms of x or y. Last week we had a delta y. So we had to write the radius in terms of y. Then this becomes a definite integral when we evaluate this expression at all the values of y. And then so the last thing that we had to decide was the values of the delta variable over which we integrate. All right. So that was our procedure. You know, we're going to use the fact that volume is cross-sectional area multiplied by the height. In this case, when we're sliced perpendicular to the axis of rotation, we're creating cross sections that are circles. The delta variable is how those little circles are getting thinner. Then we need to write the radius in terms of the delta variable. Then we need to figure out the values of the delta variable for which we have a slice. Let's take this region with the parabola and rotate it around the line y equals 9. Let's find the volume of the solid. Formed by rotating the region so we're going to use y equals 9, that top boundary, as our axis of rotation. So we can try to imagine what this is going to look like. Last week, we had a section of a circular paraboloid. This one is not going to be that same shape. For the circular paraboloid that we calculated last week, the bottom of that was flat. If we rotate this region about the line y equals 9, we're going to have a pointy bit right at the end. So it's not going to be rounded and flat. It's going to come to a point. So we're imagining rotating this way. So there's our original region. Last week, our circular parabola had a rounded bottom. We should notice that on this solid, there's a pointy bit. So we don't have just a wider version of the same shape that we had last week. We're also rotating this vertically. But that's all a matter of perspective. It's still just a bowl. But this bowl, instead of having a rounded bottom, this bowl has a point on the bottom. All right. So let's imagine a typical slice. If I imagine a slice I want to see where that slice comes from in my original region. So I want to think I'm going to slice this perpendicular to the axis of rotation. My axis of rotation is horizontal, y equals 9, and I'm going to make vertical slices. That means I'm going to have a delta x. Let's see what one of these typical slices looks like. So here is the slice of the region that rotates into a circle. There's the slice that rotates into a circle. The slice is perpendicular to the axis of rotation. So this gets rotated into a circle, like we see down here. That red line gets rotated into a circle. So we need to identify the delta variable. We're going to imagine these circles being very thin, and so the delta variable is how where we are slicing them to become thin. So this is going to be delta x is going to be our delta variable. Here's our slice getting thinner. And that is a change in x. The volume of the slice is pi r squared times h, pi r squared being the cross section. So we got to go in here and identify what the radius is. The radius is always measured from the axis of rotation to the other end of the slice. So there is where we will have the radius. Now I need to write the radius in terms of the delta variable. The boundaries are defined by relationships between x and y. So I have to identify where x is and where y is. So if I pick a point on this y equals x squared, here's where x is from the origin horizontally to that slice, and y going to be the vertical distance of the origin from the origin to the slice. Last week, the radius was just equal to x. We had to write that in terms of y, but the radius was just equal to x. Here, the radius is not equal to x or y. Y is this distance down here at the bottom. The radius is this piece up at the top. So I need to write the radius in terms of y. Since the y is the distance from the x-axis up to the slice, What I want is the bottom of the slice at the top of the slice, and the top of the slice is at 9. So for the radius, we're just going to say the top at 9 minus the bottom, y. So the radius is 9 minus y. But the delta variable is delta x, and I need to write the radius in terms of delta x. Fortunately for our heroes, the relationship between x and y is that y is equal to x squared. So I've got all the parts I need. I've got the radius is 9 minus x squared. The delta h is the delta x. All I need now is the values of the delta variable for which there is a slice. And since it's a delta x, I'll integrate from 0 to 3. So my volume of the slice is pi times the radius squared times the height. My total volume will become an integral. I integrate over all the relevant values of x. The slices start at 0 and the slices end at 3. So my V total I'm going to factor out the pi like we do. The integral of the radius squared times the delta variable. The radius is 9 minus x squared. The delta x becomes dx when we switch from discrete to continuous. And the values of x in play are 0 to 3. As you know, since we're learning how to integrate, we should always integrate by hand. So take your hand, grab your calculating machine, and ask it for pi times the integral of 9 minus x squared with respect to x from 0 to 3. Double check our syntax. And then see what we're right. 407.15. I usually request 5 significant figures for reasons. I had to pick something. I never assign units. So 407.15 cubic something. I don't know exactly what the units are going to be, but there will be 407.15. We should suspect that this is some fraction multiple of pi. If we drop the pi out of there, it's 129.6. So as a fraction, 648 over 5 pi. Sometimes you'll see exact answers only. That would be really weird to require it be in this form. One thing you're definitely not going to do is put a decimal multiple of pi. I don't know why this bugs me so much. I might be the only person. I might be the only professor for which this makes me mad, but don't do that. Pi is, if you're gonna start decimals, if you're gonna play decimals, just go all in with the decimals and multiply out by pi. I know in this case, the 129.6 is a rational. Works out nice and rational. So there won't be any square roots involved. So it's tempting to just write 129.6 and I just go full decimal. Because what's going to happen is you're going to write 129.6 and then forget to write the pi. And I'm going to see that on your paper. And I think that is so tragic because I know all you forgot to do is write pi. And I make you do the problem all over again. Figure out why you got 0 points. Remember, you get all 4 points back by just coming back and putting the pi at the end of it. Taking another picture of your work, uploading that. Any questions? So both of the problem that we did last week and the problem that we did here, are strategies with the slice perpendicular to the axis of rotation. And that produced a circle as a cross section. So we did pi r squared for our cross section area. Now, the reason that we got away with just a circle on these problems is that the axis of rotation was actually a boundary of the region. So we need to consider, what if the axis of rotation is not a boundary of the region? Remember, this is an analytic geometry series of questions that we're answering. It's less about calculus, it's more about analytic geometry. When you're doing math, if you're having trouble setting up the problem, that is correct, because setting up the problem is the problem. The reason that we just do this is because setting up the problem is the problem. I already know that if I ask you what the antiderivative of the square of the difference of 9 minus the square 9 and the square of x is, I know that you know how to do that. You just multiply it out, take it a term at a time. Some of you are really dedicated to that. I gave you a substitution, but you multiplied it out. Michael, that's commitment to the bit. So well done. So let's do the same region. So the change here is that the axis of rotation is not a boundary of the region. So the change here is the axis of rotation is not a boundary of the region. That's the big change. We are still going to slice perpendicular to the axis of rotation. We are still slicing perpendicular to the axis of rotation. So I've moved my axis of rotation down here to the x-axis. I'm still dealing with the same region. But now we notice the axis of rotation is not a boundary of the region. So when I draw a slice of this region perpendicular to the axis of rotation, it's not going to be connected to the axis of rotation. So we're not going to be, the slices are not going to be circles, not solid circles anymore. The slices are going to be circles with circular holes. And we usually refer to these as washers. It's going to be a circle with a circular hole. Because we're not rotating about a boundary of the region. So this original piece will show up here and get rotated around this axis going through the center, which is the x-axis. So if we think of the other parts that are attached to this circle, the top out here is the y equals 9. And here is where we'll hit the parabola. So we'll have a similar shape. We're going to have a solid with a hole in it. So notice on the outside, we're taking this cylinder and we're just drilling this hole going down to the center of it. I usually don't attempt to draw these. You can see why. First of all, I know I'm going to go after this with equations, so I'm not really concerned about what it actually looks like. Second of all, I'm just not very good at drawing them. Third of all, evidence that I'm not very good at drawing them. This is one of the best ones I've ever done. So, I mean, geez, if that's the best one that you've done. Yeah, that's the quality of my work. This is why you shouldn't take me for Calc 3, because it's going to be multivariable, it's going to be solids, and I ain't going to draw them. I'm going to say this is a bunch of equations. So what we're going to do is we're going to take the outer circle and subtract the inner circle. So the volume of the slice is going to be in 2 terms. I'm going to have two radii, a big radius and a small radius. I can use the same H for both, because we're just going to take this washer and make it into a little tire. So we're going to clean things up a little bit, because both terms have a pi and both terms have a height. So I'm going to factor a pi and a height out of both terms. And so I have a circle with a hole in it, a washer. Our volume of the slice will be pi times big R squared minus little r squared times H. H is still going to be the delta variable because these washers are getting super thin. Now I just need to write both of these radii in terms of the delta variable. So we've got our formula for the volume of the slice. And we're going to use this formula whenever we are slicing perpendicular to the axis of rotation. And the axis of rotation is not a boundary of the region. Since I'm slicing perpendicular to the axis of rotation, my height is good. My delta variable is going to be delta x. Oh, since I'm slicing perpendicular to the axis of rotation, and the axis of rotation is the x-axis, a horizontal line. Delta x is our delta variable. Now I need to go in, identify what my little radius is and what my big radius is. If we're going to call something a radius, it has to be measured from the axis of rotation to the slice. So if I start with the axis of rotation, go to the near end of the slice, that's my little r. And the axis of rotation to the far end of the slice is the big R. Anything that you call a radius is got to be measured from the axis of rotation. That's what makes it a radius. So notice that for all these slices, big R is always going to be 9. So that's handy. Big R is equal to 9. Oh, little r is going to depend on x and y. So I need to locate a point, identify where x is and where y is. Make sure I label x and y. I didn't have to worry about that with big R because big R in this case was always 9. Little r is just equal to y. Notice that little r is the distance from the x-axis to the bottom of the slice, and that's right where y is equal to, or that's right where y is. So little r is equal to 9. So my volume of the slice is pi times the big radius 9 squared minus the little radius y squared times the delta variable delta x. The last step is to put this into a Riemann sum and then turn our Riemann sum into a definite integral where all this continuous, this discrete stuff becomes continuous. And then the last step is to decide, well, I guess the second last step is to decide what values of y, what values of x produce a slice. So the v total. I'm going to factor out a pi, and I'm going to simplify 9 squared minus y squared. My discrete delta x becomes a continuous dx. And that's how I skipped the thing. What did I skip? Yep. R is still in terms of y. I don't want R in terms of y. I want R in terms of the delta variable. So R is equal to y, but we have delta x. Yet another casualty of daylight savings time. I need to write the radius in terms of the delta variable. So R is equal to y from the diagram. And I have to convert y into x with y equals x squared. So the volume of the slice should be pi times 9 squared minus x squared squared. Oh, wait, no, I didn't need to square that. All the rest of the stuff that I was saying before I built the definite integral, that stayed the same. But I couldn't keep talking because clearly changing what time it is, moving this class to 7 o'clock in the morning, messed with things. Like things are worse than they normally are. I mean, normally I'm fairly focused. And now, of course, people could always say, well, just go to bed an hour earlier, as if that's how this works. As if that's how sleep patterns work. If we could just go to bed an hour earlier and like that worked, no one would complain about daylight savings time. It clearly doesn't work that way. You don't just decide to go to sleep an hour earlier and have that work just as well as normal. We are creatures of habits. We like our patterns. And when you muck with those patterns, we get eaten by lions. That's just how it goes. Yikes. Any questions? So we're going to pi times math 9, 81 minus x to the 4th this time, with respect to x from 0 to 3. We expected it to be bigger because the we've I was thinking of a different problem. Never mind. We expected it to be bigger for reasons. I was thinking of the next one and why we expected it to be bigger. Here's the problem to practice on. So problem, to practice on the problem that we're gonna do tomorrow, I'm gonna use the same region. And now I'm gonna rotate about the line y equals 11. So perpendicular to the axis of, we're gonna still slice perpendicular to the axis of rotation. But now our axis is not a boundary of the region. And in this case, our axis of rotation is going to be above at y equals 11. Our slice still has to sit inside of our region. Do all the things. Label your big R, label your little r, label X and Y. All right, that'll do it for today. I will see you all on tomorrow. Everybody have a good day and thanks. Bye.